Welcome to lecture number 58, and we have been discussing about rotating DC machines, formal type of DC machines as we understand and used in practice. And in my last lecture I just told you what are the basic structure in a very rough sketch, but it brings about all the important structural features of a DC machine. For example, the stator will have two projected poles if it is a two pole machines p equal to 2. There may be multiple number of projected poles if the number of poles of the machine is higher, and this part is almost a solid piece of iron over which there will be coils with red colors. These are called field coils. One of the simplest stator coils are no complications, just take wires and make this coil over the projected poles, and these two can be suitably connected so that when you pass DC current in it, this produces north pole south pole, because this is the direction of the current. So, lines of force will come out from this like this and it will enter here, creating the south pole, and these lines of force will complete their path through the stator iron like this. A sample lines of force will be, and the armature is a number of circular thin plates made of soft iron, and they are stacked together so that you get the length of the machine, which in this case will be perpendicular to the paper. Similarly, this projected pole is also having a length perpendicular to the paper. Anyway, so this is the basic structure, but the armature is slightly complicated, and why it will be complicated, that we will discuss in detail, do not worry about that. But essentially armature has got slot and teeth where there will be conductors placed. Okay. And this field will be excited by some DC source, and this field current is often denoted by IF, constant value DC current, and depending upon the strength of this field current, these are essentially electromagnets. The strength of the value of flux density in the air gap will be decided. So, lines of force will be completing their paths through the stator iron, cross the air gap, armature iron, cross the air gap, and back to square one. So, this is how the field is created. Now, our concentration will be about the armature coil. Now, armature coil is in my electrical machines 2 lecture, I have discussed in the winding portion of the course the basic terminologies used in making a winding. Okay. And I will go rather quickly here to tell you about that. Okay. But you can, if you like, please see those videos whose links will be given in your website for this course. Now, we must understand that the rotor being a structure, rotor will be like this. There will be slot and teeth, all along the rotor. This is the rotor, only a portion I am drawing, and I will place a conductor here, which will be take a piece of wire, put in one slot, at the end you turn around, and through another suitable slot you bring out this end. So, at the and you will have two terminals for this coil. Okay. And you can of course have a multi-turn coil, that is, you take this wire, single wire, come here, then once again repeat this. So, a multi-turn coil will look like this one. Take a piece of wire, this is one slot, it goes, it at the end it will be like this, and then make several turns like this, another turn. It is a two-turn coil. And two terminals will be there, and this is a coil, okay, and this coil has got two sides. This is coil side 1, coil side 1, and this is coil side 2. And this coil physically will be placed in the two slots. I am sorry, I have put it in the teeth, it will be actually in slots. So, it goes, comes back, like that and comes back. So, in these two slots, suppose this coil is placed, it can be placed around that, and this can be understood in this way, that suppose these are the slots here. Suppose this is the slots, these are the suppose slot and teeth, and just a this simple thing, and then you have a coil. Anyway, this you see, just this is the teeth, this is the teeth, these are the slots, and therefore, this is one coil. This is one coil side, it goes along the length, then it comes back, and it has got two terminals. Similarly, another coil, it has got this coil side, it goes around and returns, and two terminals for the second coil, and so on. Is that clear? Physically, a coil will look like this, a practical coil. It is just made two turns coil. You take a piece of wire, on a format you make this, two times you go around, and these are the two terminals of the coil, these two, clear. And this what I will do, I will place it in one slot, this coil side, and the other coil sides at some appropriate slot. Arbitrarily it cannot be placed. Okay, this is how the coils will be placed. One good information is all coils are identical. Okay. This is one coil, another coil will be also placed in these slots, only displaced from the first coil by some space angle, that is all. But the idea is very clear. So, each coil will look like this, and it will be in this fashion. Now, the question is, so each coil has got two coil side 1, coil side 2, that is what I have written here, coil side 1 and coil side 2. This is how I have tried to, and it is almost like a diamond shaped. The effective length of the machine is this one, which will be under the influence of the north and south pole, and these portions, that is this portion and these portions, are called overhang of the coil, overhang. There no voltages will be induced, because it will be under the purview of the magnetic field produced by the stator when it will be running. Now, the big question is, where this what should be the difference in number of slots between these two coil sides. So, two coil sides make a coil, remember this, two coil sides make a coil. With two very distinct terminals, that is all, and all coils are identical. Now, if I ask you this question, that consider a simple two pole DC machine, that is here. This can be easily understood. Suppose field coils I am not drawing, it has created north pole and south pole, and here you have the armature, and there are one slot here. And you have a coil side here which is perpendicular, and by coil side I know where it is part of a coil, one coil side. Suppose this is coil side 1, what will be the induced voltage in it? Suppose this armature is moving in this direction, it is like this. So, induced voltage will be, you have to apply right hand rule, B, V and L. So, this will be, cross will be the induced voltage, or if you change the direction of rotation, suppose it is moving in this direction, then the induced voltage will be like this, B, and V is this way, this is the direction of B, north to south lines of forces are, and your this coil side will, I will show a dot to indicate the induced voltage polarity, is not BLV. Now, this is a single conductor, but to make it a coil side I must it must have another coil side like this here. Therefore, what you do is this, you suppose there are two slots which are diametrically opposite, and this is one coil side and this is another coil side. Okay? That is coil side. I was telling now where the coil side should be placed. Suppose it is a two turn coil. So, one coil side is here and the other coil side, in which slot should I place? There will be number of slots. I will place it so that induced voltage in the coil becomes maximum across between these two terminals. Suppose it is in generator mode, if it is running, there will be induced voltage in this conductor cross and in this conductor it will be cross, because velocity is this way, B is this way, you can once again apply right hand rule. So, what happens is this, the polarity of the induced voltage, this will be plus, this will be minus for this coil side 1, and it will be minus, it will be plus if it is coil side 2 like this, because it is under south pole having same velocity. Therefore, across this coil, this is the induced voltage in coil side 1 with this polarity, this is the induced voltage in coil side 2 with this polarity. So, you will get 2 BLV as the induced voltage between these two coils. Clear? Therefore, you must place the coil sides of a coil intelligently, so that across the coil, if you allow that coil to move relative to a magnetic field, the induced voltage in the coil becomes maximum, which ultimately told in a different language. I will always say that if one coil side at a given instant of time, if it is under the center of the north pole, the other coil side must be under the center of the south pole at the same time. Okay, it will rotate after some time. If it is rotating, it will come here, this will go there, but it is still under south pole, maybe at reduced strength, but once again the voltage will be 2 VLV, maybe the magnitude will not remain same, is not. Therefore, the essential consideration is that if this coil side, to check you have properly placed it or not, imagine that one coil side, if at a given instant of time is under the center of the north pole, the other coil side of the same coil must be under the center of the south pole. This is how we tell that. If that is the case, then you check the maximum induced voltage here. For example, if somebody says he has put the two coils, he has made a coil and he has put it like this. This is, there was a slot available here and there was a slot also available there. And it is a two pole configuration like this, north and this is south, and he places one coil side, he makes a coil such that one coil side is here and its return coil side is here. When the center, when this coil side is under the center of the north pole, the other coil side is in the magnetic neutral zone, B is 0 here or tangential to the velocity. If velocity is this way, can this conductor produce voltage? No, because B and V are along the same lines, B is from left to right. Therefore, in this case, of course, at this instant there will be induced voltage. Under this condition, what will be the nature of the voltage? Nature of the voltage will be like this. This will have a induced voltage like this BLV, and this will have 0 voltage, this coil side. So, you will get voltage across the coil, but only BLV. So, that is why you always insist upon that for a given coil, if one coil side is under the center of the north pole, then other coil side must be under the center of the south pole. That will tell you in which slots the coil should be placed. And as I told you, there will be number of coils, number of slots, but all coils are identical. Okay? In different slots, you go on putting the coils in a particular fashion. That is that's all. So, this is like this. If you have understood me, then you should tell what happens if it is, suppose the machine is 4 pole. What do I mean by 4 pole? 4 pole means on the, I will go to next page. 4 pole means, suppose on the stator there will be 4 projections. This is your stator. I mean not very nicely drawn, but it will give you the idea, and this is the stator iron. So, if you and suppose this is the sectional view of those coils. So, there will be now 4 field coils. Got the point. So, I want to make this is not. So, the currents are like this, cross dot here. Then the next poles will be a south pole. So, lines of force will go in, therefore, it must have cross here and dot there. So, that it will become south pole, and this one once again cross and dot. So, lines of force will enter. Oh no, this I have to make this cross, and these will be dots. So, that once again it will become a south pole, north pole. That is, here lines of force were coming out, here also lines of force will. So, alternately you have to create the poles, north, south, here it is north, there I want to make it south. So, it must be cross and this should be dot and lines of force will go in. So, lines of force will complete their path like this, north, south, north, south, and this is north, this will also create a lines of force like this, and this will also create a lines of force like this. So, north, south, this is the thing. So, and this field coil should be connected in series in such a fashion the current distribution in these conductors is like this, then only this pattern will be created. Okay. If that be the case, then in this simplified diagram, now I will not show the coils, I can create a 4 pole stator as simply as this with 4 projections with conductors around it, and so suppose you have created these poles north, south, north, south, then it is called a 4 pole DC machine. Full stator I am not drawing. Now, on the let us come back to the armature, which is a circle with lot of slots and teeth. For example, here is a slot. Here is also a slot. Okay, and there is also a slot, like that it is available, and there are many other slots here, there, many slots are there. Okay. Now, I say that okay, I will make a coil like this as usual. If this is coil side 1 of a coil, where do you like to have your other coil side? Should it be here, diametrically opposite? If you make a coil whose span is this much, that is this coil side and this coil side, then across the conductor there will be induced voltage, but the polarity of the induced voltage will be subtractive, and across the coil you will get 0 voltage. That is why the rule is, that is, you must ensure if one coil side is under the center of the north pole, the other coil side must be under the center of the south pole to ensure that maximum voltage is induced. Okay, so this is how the coil span, this is called coil span. Okay. So, this is the thing. Okay. Then a coil span, I will always say it should be equal to 180-degree electrical. Now, the question is what is 180-degree electrical? 180-degree, whenever we say angle, we say in mechanical terms we understand. For example, 90-degree is this, is not, and 180-degree is this. These are all mechanical angles. Now, what do I mean by 180-degree electrical? The idea is simple, it is like this. That is, if you imagine you have a two pole structure like this, and you have a single conductor suppose a single conductor and you allow it to move with certain velocity or n RPS equivalent to that. If it moves, the voltage across this conductor in this position it will be 0, is not, because B and V are on the same line. It will be having some maximum value when it comes under south pole, then once again it will be 0, then once again it will be maximum, but polarity will reverse because it is now under north pole, and once again back to 0. Now, listen me carefully. If this conductor makes a complete 360-degree rotation, your output voltage across this conductor means across this coil side, other coil side I have not drawn, I could also draw that. Okay. Or if you feel put another coil here, other coil side. So, voltage across the coil is 2 BLV at any time and it will be 0 here, then either positive maximum or negative maximum. So, with respect to time, if you sketch it is 0 here, then it attains some positive value. Is not, when this fellow comes here it will have some positive value, say, then when this fellow comes here it will have once again 0 voltage. So, like that it will grow by some rule, but anyway it will have a peak back to 0 here. Then when this conductor makes a complete rotation of 360-degree mechanical, you will get one cycle of EMF generated across the coil. AC voltage will be generated, BLV. But if you have a 4-pole structure, like this, north, south, then once again north, once again south, and I have learned what where this coil should be placed, coil should be placed here, one conductor, slots I am not drawing, it will have two coil sides and you allow it to rotate. So, if this arrangement rotates by 360-degree mechanical, 1 RPM, 1 rotation, mechanical rotation will ensure what? 2 cycles of EMF, because it will undergo north, then south, then once again north and then once again south back to north. So, one complete rotation of the rotor will induce 2 cycles of EMF here. That is one rotation, one mechanical rotation will induce two cycles of EMF. Here in two pole configuration, one rotation, one mechanical rotation will induce one cycle of EMF. Got the point. So, here the conductors or the coil sees only two poles, north south, one cycle of EMF. In this case, coil will see north south, once again north south, till it makes a complete mechanical rotation. Therefore, this angle for electrical induced voltage is the theta electrical, that is 360-degree electrical, is not, and this is 180-degree electrical. In case of mechanical two polar machine, we see that theta electrical is equal to theta mechanical, no difference. Angle in theta electrical and theta mechanical. When you plot sketch the voltage in terms of theta, theta is omega t, it will become eventually. So, it will be like this. So, in this case I will say theta electrical must be equal to how much? P by 2 into theta mechanical. That is, you move by 90-degree means we have moved by 180-degree electrical. So, think about this. This is very basic concepts that I will use while discussing about the armature winding of DC machine, and understanding of this is essential, you cannot avoid. And better look at the detailed introductory part on the winding lectures of my electrical machine 2 course. I am briefly telling, but rather quickly, because no point in repeating the same stuff once again, which is already available. So, see that ideas are simple. So, I must distinguish between electrical and mechanical angle. Number of poles of a machine will be always even, it cannot be odd, because you cannot have a monopole. If there is a north pole, accompanied south pole must be there. So, I have indicated the basic idea of this, and next time we will continue from here. Thank you. এই আজকে থাকা কালকে আমার